Okay, so let me just start off by reminding you my web page. The top thing there is for this course. If you click on that, you'll see that there's a new reading assignment. So I will talk a little bit about this new paper by a recent set of slides by Andrew Chen, who's a computer architect. And he introduces a concept called 10 by 10. And I'll explain what that is a little bit from the Salishan conference in April. And you can find it online. If you don't find it online, I can send you my copy. But anyway, if you use Google and put those words in it, you should get right to it. It's just a PDF that's online. And then also, the lecture notes have been updated. And each day I'm going to update it. There'll be more and more. You may have noticed that it didn't go much past what I talked about last time. And the same thing will be true today. So you'll want to pick up a new version of the lecture notes. And so I urge you to do that. And feel free to do it now if you want to follow along. If you do that, what you will find is here, and you'll want to start, let's see what slide this looks like. 55 is where I'm going to start off. And, oh, wait, there's an update available. A newer, what's this? How do I get rid of this? Good, okay. So, I just want to make a comment. Someone looked at these numbers and said, but wait, how do you claim this is scalable? And I just want to make a little, here's the caveat. I introduced the notion, there were a whole bunch of notions, and we ended up with this notion of weak scaling. And what I want to say is, I'm not claiming this algorithm, this combination of algorithms. There are two algorithms here, the U-cycle multi-grid, which goes down part of the way on a V-cycle and then goes back up. And then PSOR is the solver on the course's level. And I'm not claiming that that combination is actually scalable. It scales well up to this level, but as you can tell, for much larger problems, you'd have to do a different strategy for the course level solve. This PSOR is not going to hack it when you go to much bigger problems. So the point here was not to claim that it is scalable, but to get the right metric to use to look at it. So the scaling, the weak scaling notions were the way that we used to figure out what's going on. And the key point in that is that maybe I do need to go back a couple of slides just to show you what it is. The key point here has to do with the choice of the problem size given the number of processors. So we keep the same in this particular case, because multi-grid scales linearly in the number of unknowns. We keep the number of unknowns the same for each processor. If you were doing something else, you'd have to figure out what the right scaling law is. But that's what weak scaling tells us to do. And when we do that, we're looking at something that we're hoping to be constant, and that's it's as constant as it is. It's pretty good, 3.8 seconds up to 4.1 seconds. So we feel that's pretty good. But the main point here was just to introduce weak scaling tools as a way to analyze this problem, because the strong scaling, you would never be able to do a problem of this size on a single processor. So you'd be stuck. And
so are you changing the grid spacing along with the weak scaling?
Yeah, I mean, the point is that as the number of processors goes up, so does the grid size.
I understand that. So
yeah.
You're making the same physical dimension, and therefore you're changing the grid spacing.
Right, right. Yeah. So it's a billion unknowns for. Yeah. Okay, all right. Well, that was what I wanted to do. Now, another thing that I wanted to say here is a little caveat about the whole business here. So what we're really about is, as Hamming said, we're trying to get not numbers but insight. And we're really trying to solve technical problems. So I take that as the top level issue. We have a technical problem to be analyzed. Notice I said analyzed, not computed, but analyzed. So how could you do it? Well, there are a lot of things that you could do. There's a tree. You could just go out and consult with experts on the topic, and they might give you insight that would give you all the information you really wanted to know. So you wouldn't have to do anything but just talk to people. You could go to the library and look up things in the library and come away with insights that might be more valuable than anything else you can do. There are, if you decide you're going to try to model it, there might be different models that you would pick. And a lot of the work that I've been doing recently actually is on the modeling level. And one way to say it is that at a certain point I decided that people weren't really asking me about how to solve their equations better, but what better equations to solve. And so you can win a lot more by solving better equations than you can by solving equations better. So I encourage you, when people come to you and ask you to collaborate on it, talk a lot about the model and make sure that that's not where the problem is, that the model isn't the thing that's wrong. Because, you know, when you discretize, you can improve the answer by order h, but when you change the model, you change it by order 1. And that's a big change. So always consider that there are different models that could solve the overarching technological problem. Now, once you've looked at a model, you might say, well, there are different discretizations that could be involved. And there is a famous model for surface water waves that I've been involved with over the years, the kind of model that predicts the propagation of tsunamis. And the Korteweg-de Vries equation is a very famous equation for modeling that, but there's an equally valid model that is easier to compute with. And so we've done this comparison in that sort of setting. And that often is a comparison that's available to you. There'll be different discretization, there'll be different models, there'll be different discretization techniques. Some models will have discretizations that work very well, and so forth. So you need to consider all of these different issues before starting to program. And then ultimately you may find that the model that you're forced to work with and the discretization that you seem to be forced into and so forth requires a huge mesh. And now you say, there's only one way I'm going to do this, by parallel computing. So then that's where we're back to the topic of the conference. But I wanted to say that this is the big picture. And so sometimes there are different ways to proceed. Okay, so now I'm getting back to the list of topics that I advertised. And I wanted to talk about computer architecture a little bit. And this is the notation that you see. When you see a picture of a GPU and there are all these boxes and connecting lines and so forth, what's being used is a well-known notation called PMS, for Processor Memory Switch, that you can read computer architecture books that introduce this. This is a very brief summary of what the idea is. But the idea is to look at components that do different things. So the processor does some sort of operations on data. Memory stores information in either instructions or data. And then switches are things that connect the components. Now, in the full PMS diagram, there are more letters than that. There are controls and different things. But we can go a long way with just these 3 letters, P, M, and S. And so I want to show you what that looks like. So here is a very simple picture where we've got 2 processors, 2 pieces of memory, and a switch connecting them. And what I've got here is just something that can add and multiply, a couple of registers, and a bus connecting them. I don't know that this could compute very much, but anyway, you get the idea that you've got these kinds of components. The plus and times are what we call processors. The bus that connects them is the switch, and the registers are the memory. So that's just some sort of simple CPU that might not do very much, but that gets an introduction to the notation. Here is a much more sophisticated computational device. This is pretty close to what you have in a laptop like this. So you've got a CPU, and you've probably got a memory management unit with the cache, maybe multiple layers of cache, but let's just take the case of one cache. Then you've got a bus that connects to main memory as well as other devices, of course. Now, this memory management unit itself is a processor. I don't know if you've ever thought about how cache works, but when you make a memory reference, it goes to this memory management unit to decide, is the memory here in cache or is it out here? And if it is in cache, it just gives it back to the processor. If it's not in cache, it has to go out over the main memory, over the bus, and puts it in cache as well as giving it to the CPU. But you see, it's a processor memory switch description. Okay, so that's what a typical processor today looks like. And now we can talk about some more interesting architectures, parallel computers. Here is a shared memory multiprocessor. You've got a CPU, you've got a cache, there's a switch, some sort of memory bus that connects to a shared memory. Now, the conference is mostly about GPUs, and if you look at pictures of GPUs, you will see this is one component of the design of a GPU. And so anything we can say about this, there's a lot known about these classic shared memory multiprocessors. This is where it all started, in a sense, on the commercial side. And a lot was learned about this. In particular, it was learned you better put a cache there because this is the bottleneck in shared memory. Getting to the global memory is the thing that's the limiting issue. And one way to say it is there were very few commercially made processors that went above 32 processors. And so what does this say about the future of computer architecture? It's not so clear. I would be surprised to see multi-core processors with 2,000 cores on a single shared memory bus, but you never know. Anyway, whatever we can look at from previous experience with the shared memory multiprocessor will inform the discussion about how GPUs are designed and utilized, and also with multi-core architectures. A major problem here, of course, is cache coherence. If I make a change over here, if I write to memory, you got to decide, well, do I just change the cache or do I force it out into memory? And there's a huge industry developing that technology. But that's one of the problems with caches. It's not so simple to utilize them. One of the things about the shared memory processor that you can do is you can prove a theorem about the amount of speed up that's possible based on this work-to-memory ratio. And essentially this theorem says if you got to go out over that bus, there's only so much bandwidth on this shared bus. And so it doesn't matter how fast these processors are. If everybody is in contention for memory, there's a limit to how much speed up you can get. And so it depends on how much your work-to-memory ratio is. So if you can come up with algorithms that are better, you can get greater speed up. But in any case, there's an ultimate limit given by this theorem. As I say, both GPUs and multi-core chips use this basic shared memory architecture, so there is a lot of information that can be brought to bear, a lot of experience with shared memory machines. Ultimately, it's going to come down to, can you come up with better algorithms for getting a better work-to-memory ratio? And that I'll talk a little bit more about that. The bottom line is that the experience from the past is you had to have a different architecture to scale up to hundreds of processors even. And what was that architecture? Well, one architecture is to use distributed memory. So you have a network connecting processors. Each processor has its own memory. So this is a typical network of workstations, or many other commercial processors have been built like this. If you wanted to connect multiple GPUs, it would be something like this. And there's some sort of topology that connects these things together, some sort of graph that connects the different processors. In a sense here, I've left off the letter S. The switch is this network. That's where the switch is in a distributed memory multiprocessor. Okay, so a little bit of the history here. You know, it's all about the networks in those architectures. So people came up with 2- and 3-dimensional meshes, and other graphs were proposed. I should say this is a simple ring topology. That's essentially the simplest I know of. You just put things around in a circle. When you do a 2-dimensional mesh, you can wrap around and then you get a torus, and you can have a 3-dimensional torus that wraps around. But other graphs have been proposed. Hypercubes were used commercially very early on, and those remained viable for a long time. Crossbar switches are things which connect everything together. A simple hub, Ethernet hub, looks like, the way you use it, it looks like a crossbar switch. There's a thing called a multi-stage interconnect, which has been used in a number of commercial applications. So there are lots of different networks. Hypercubes are kind of fun because there's a lot of math, I think. And so, but as I say, there were a number of, N-Cube was one of the first commercial parallel computers, and it persisted for a long time and was eventually bought by Oracle. And I think that's our dreams. Everybody wants to be bought by Oracle, right? Or some other, you know, by Google or something. But so they did very well. And so the idea is that the network here is the vertices of an n-dimensional hypercube. You can parameterize it by just zeros and ones in the appropriate dimension. And the nice thing is that the bandwidth scales up as the dimension increases. The bad thing is that to get a bigger machine, you have to buy twice as big a machine. You can't buy a 50% bigger machine, so you had to double your budget to go to the next largest size. There's a related related graph called cube-connected cycles. One of the difficulties with the hypercube is that each individual node had to have enough connections to make all these d-dimensional connections, and so you were limited by how much you had built in when you designed the individual processor. This used a hypercube, but used at each node of the hypercube a cycle, so you had to have fewer, in other words, a ring of processors. So if you could support 3 connections, you could build cube-connected cycles. So this sort of thing could be, you could build a hypercube-like topology with just off-the-shelf technology. It's something I've always wanted to do but have not yet implemented. Okay, so there are a wide variety of topologies. They all have a similar model for communication. There is a latency of communication that's rather high to go out over the network, and the rate of communication is given by some sort of bandwidth parameter. Networks of workstations took off with this topology, and you know, became the norm in parallel computing up until the arrival of GPUs. So with this notation, you can start to compare and contrast different architectures. And I've given 4 here that are more historical, perhaps, but they include the kind of vector supercomputer that dominated high-performance computing until 15, 20 years ago. And it was characterized, so the gray areas here represent the switches. And they were characterized by having huge bandwidth to memory, very expensive. On the other hand, with, say, a network of workstations, you've got relatively slow, so they're narrower bandwidths to a switch connecting to the other processors. So the width is meant to be the bandwidth, and the distance maybe is the latency. These are very low latency These are fairly high latency. And here's the shared memory multiprocessor, which you can now easily compare and contrast with these other two architectures. And I put up another one here just because it was a very good idea, something John Hennessy worked on for many years. And it's a cache-only memory architecture, so-called COMA. There was a commercial version of this, Kendall Square Research, that I was fortunate to get to have in my own lab and use, and it's very interesting. So let's just say a little bit about how that works. So the idea is that it's all cache. There is no main memory. It's just everybody's got a huge cache, and you're connected to this device, which is called a directory, which keeps track of where things are. So it's really a shared memory architecture. It looks like this, but notice this box is sort of now empty, or it's rather just a thing to tell you where the other caches are. So it's an interesting architecture. Has lots of advantages, and unfortunately the disadvantage of needing this rather expensive directory system. Let me go back. So yeah, so here's this is kind of the figure caption is here when you're going back to review this. This figure allows you to contrast lots of different features. And for lack of time, I won't go over these in detail, but I'll leave as an exercise to compare and contrast GPU and multi-core architectures with each one of these, because I think it will help you understand how these are designed, and it gives you a way to compare them with other architectures for which we have a lot of experience. Here are some merits and demerits of these different designs. The problem is that different algorithms perform differently on all those different architectures. So this is, even if you have a language which allows you to port to different architectures, the algorithms themselves will not always behave the same. And so you have to be prepared for that. So shared memory multiprocessors don't do very well with things with small work-to-memory ratio. That we saw in a theorem. Networks of workstations, on the other hand, if you have very small and frequent memory transfers to other processors, they don't work so well, whereas shared memory does pretty well with that. The memory, getting memory from one processor to the other is just a write to memory, a very low latency operation. The vector supercomputers, which only a few of us in this room can remember, but they were the dominant, the Crays were the dominant supercomputer, the first supercomputer and the dominant one for many, many years. They had massive bandwidth to memory. And that made them relatively easy to use. That was an issue that everyone was aware of, that if you had to give up on vector supercomputers, you're going to have to pay a lot. And parallel computers are a lot harder to program than vector computers were. So, but there was a price for it, and we seem not to be able to, we don't seem to be able to pay that price anymore. At least that's, nobody has figured out a way to sort of roll back the clock on that. COMA, which has disappeared from the scene for the moment, had interesting benefits, but the cost was this complex memory system or directory that had to be provided. Okay, well, that's the past. I say that just to encourage you to think about the GPU architectures and other current architectures by looking back at how things are designed. And I've introduced some notation, the PMS notation, which is the standard way that our computer architects talk about these things. Let me talk about the future, because that's maybe more relevant. And especially, I mean, not to knock these guys, because they've revolutionized things, but in a way this has happened in the past. Intel had a parallel supercomputer that it was selling, and at a certain point the people in the graphics chip development center came up and they said, well, we've got this chip, the i860, you could build that could be your floating point device. And so that was a big breakthrough for Intel to switch over from the lower level chips to this graphics chip, and that's when the first real parallel supercomputer was available. And then that graphics technology was incorporated into future designs, into the Pentium design. So it's a natural question to say, if you have CPUs, GPUs, multi-core, who knows what, what's the future likely to be? Well, of course, nobody knows. That's the great thing about the future. Everybody can speculate and nobody really knows. But I think one thing everybody agrees on is that energy is going to become the critical factor. And energy is already the thing that drove us away from the monolithic CPUs that kept you from running faster and faster and faster. And so it's already put limits that we know about, and in the future it will be even worse, because the problem is this: as the feature size gets smaller and smaller, there begins to be a limit, unless somehow you can lower the power of these devices. Maybe somebody will figure out how to do that. But as long as you're using current technology, even though they're smaller, they're still going to use a significant amount of power. And so you can't have the whole chip lit up, because that takes too much power to do. And so there will be what people are calling dark silicon on every chip. There'll be a substantial amount of the silicon that won't be used at any given instant. Now, one answer is that that will be memory, that the future would be massive amounts of memory on chip, so cache on chip. That's one possibility, so that you would, say, have a CPU or a GPU, and there would just be a huge amount of memory, and that would be very nice. It's always nice to have a lot of memory that's rapidly addressable. But Andrew Chen, who's a computer architect and the author of this paper I asked you to read on the webpage, suggests what he calls a 10 by 10 approach to overcome the 90-10 rule. So the 90-10 rule says that 90% of the computation gets done by 10% of the chip. Okay, so go find that 10% of the chip and isolate that out, and then take the other 90% and say, well, now what can I do with it? What he says is, well, build 9 other things that do something else to fill in that slot. Don't just, keep doing what we're doing. So he says we're going to have 10 specialized, that's the 10, I don't know what the other 10 is. But anyway, so the idea is to have 10 specialized units instead of monolithic whatever, whether it's monolithic GPUs or CPUs or whatever. So imagine, I don't know exactly what it's going to look like, and he doesn't either. He depicts it in terms of wrenches and screwdrivers and so forth. I'm trying to give you something to think about, so you know what a CPU is, you know what a GPU is. You probably have heard of what a DSP is, a digital signal processor. They're really fast. They do very specialized, they basically do Fourier transforms. They're really fast. Anton is a system that does molecular dynamics, so it's a specially designed chip optimized for molecular dynamics. It's not a GPU, it's not a CPU, it's a special design. And you could imagine other specially designed things which could be used for special problems. And the idea is that you're not going to be using every one of these at any one time. That would burn up the chip. But you've got to have dark silicon, so why not use this approach to utilize the dark silicon? Yes?
I was kind of wondering if you have, what do you foresee the space for something, different technologies like some of the more neuromorphic computing techniques that they had a bit in there, like the newly discovered membristors?
So the question is about other technologies. I must say I'm not a technology follower. So I know what I know, which I was fortunate to hear Andrew talk about this at University of Chicago recently. So that's why I know about it. And so I'm not a very good predictor. The question you said about neuromorphic technologies.
Membristors, nonlinear circuit elements.
Nonlinear circuit elements. Well, that's a good question. I don't know what to say. All we can do is watch and see what happens. We're largely constrained by what the computer architects, together with their marketing departments, think they can produce. So, I mean, one could also ask questions about quantum computing, and I know even less about that.
I would just add this. We have seen heterogeneous core come out, and that was the IBM and Sony cell processor broadband engine. And that was a tremendously difficult chip to program on, and it didn't catch on. Right? So if we do move to this heterogeneous computing approach, it's going to be a very, very difficult climb, or there are going to need to be different tools in place at the software level to support the computer architectures.
It's absolutely correct. I mean, the software support for these things is often what makes or breaks them. So, yes, comment.
One thing that always surprises me about this way of thinking about it is thinking about the idea that there is the computer to solve the problems. Actually, there are many, many different problems, and in most technologies, there's quite a difference between a steam shovel and a bike and a bus and whatever, a truck and so on. They're all vehicles, but they're specially designed to be particularly good at what that vehicle is designed to do. And my laptop is different from a supercomputer, so I don't see why we should be all at the same time on each computer. That's a waste of money.
Sure, that's...
I have my problem, I buy my computer,
right.
and I do it better.
This is certainly far more powerful than the first computer I used, is my cell phone. And this is not a very fancy cell phone, by the way.
You sort of want to target every problem to the same computer. But that seems to be, the Anton is great precisely because it is a designed computer for a problem.
Right.
And therefore it gets much better performance, and it's used 100% for that for which it is best designed.
That's why it's a crappy computer too, because your problem it doesn't work.
Exactly.
But it's also a function of scale.
But if you can have 100 computers in the world, they don't all have to be the same. But presumably you're going to have hundreds of thousands of computers.
Well, okay, there's another analogy I could make for a high technology. So supercomputers are very high technology, and they are not all installations of the, say, top 500 look identical. So there is quite a lot of diversity, actually. But an area where there's even more diversity and it ain't working so well is nuclear power plants. There is even less sort of this cookie cutter approach to producing workable designs, and that might there's an area where maybe this approach which we're complaining about might actually be better.
Between one of a kind and more than one kind.
Good point. Other comments? This is a good discussion. This is kind of the end of the architecture discussion. And I really, what I intended to do here were two things. One is to introduce you to the PMS notation if you hadn't already seen it, so that you can actually talk about these things in a pictorial and rational way, and then to just open up at least one possibility for what might be coming, because for sure it's going to change. I mean, that's the one thing that's been constant about computer architectures is that they keep changing. So, yes? Good question. What about quantum computing? So, I just don't quite understand what its early applications will be yet. It seems to be a long way from practical application, so I'm just not the right person to ask. I think that's a good one to save for the break and see if any. Is there anybody willing to talk about quantum computing among our simple experts here? Nobody's raising their hand. Okay.
Come on, Matt.
Okay, yes, there's a question in the back.
Well, I want to add that we're actually living, I think we're living the end of the age of the type of thinking we're doing with this type of computers architecture. As we see, quantum computing, I don't know if you have read, but what I know is another type of mind pattern, and you can solve really complex problems for normal computing just on the fly very fast, because it's another paradigm, another shift in the way of thinking. So
Right.
maybe in the next 5 to 10 years, we will be very surprised of what will really come and see as the visual solution for everyone. For example, maybe all of you have read that they can really put some big amount of memory. What really surprised me was it was really efficient and they were able to retrieve the data as the same way that they put it on.
Yes, yes. Well, and there are other optical computing is something that has been developed over a number of years. And one thing, of course, the subject of computer science takes all of this in. And there are different kinds of computational devices. An RFID, which you interact with when you go to a store and you walk out with something you haven't paid for and the bells go off. There's a device in there that's actually communicating. It's essentially a computer. One of the things that people have talked about using quantum computing, quantum dots for, is as that sort of device. So there is a very broad range of computations, and we can't say what the future is. I think it's reasonable for everybody to think a little bit about where things are going, because you have to make an investment now into certain technologies. Are you going to invest in CUDA? Are you going to invest in OpenCL or some other language or in some hardware? And it's really a good idea to know where are we going to be in 5, 10 years, so that you don't waste your investment. And of course, one of the reasons I'm talking about these fundamentals, which in many ways look sort of old by comparison, is because I'm concerned about where you're going to be in 5, 10, 20 years, and you need to have this sort of larger term perspective so that you don't just invest a whole lot in a particular thing which seems hot right now. So that's where I've been coming from. Yes?
Where does FPGAs fall?
That's a very good question. Where's FPGAs? So,
I can say a few things quickly.
yeah, please, go ahead.
Yeah. So FPGAs, for people who are familiar, field programmable gate arrays, are another technology where you can basically program an entire processor into the chip. So you have a design for logic gates for what would compose a processor, and you can program the FPGA to make that processor. And if you like something slightly different, you can modify it, you reprogram the FPGA to do something different. So you could have 10 different processors that you could just load up onto the FPGA as needed for different tasks. So where FPGAs are most prominent is in sort of integer programming, because they have very strong fixed point math. If you have something that looks like DNA sequencing or something that doesn't have a lot of floating point operations, you can think about using an FPGA, and you see really incredible speedups on these things. Because if you have a program, you can actually turn that program into a processor. And as long as that processor is fairly small, you can make as many of these as you want. Just like the GPU has many streaming cores, you can have many cores that do whatever your custom operation is, especially if it's just a fixed point computation. So for very, very specialized tasks, the FPGA does amazing things. It's probably used in cryptography way more than I know.
Yeah, you can't talk about it. You can't talk about that.
I can't talk about that, but...
So I will add FPGA to this list, because that's a very good one to do. I will say that FPGAs have been around a very long time, and all of these things, Anton DSPs, GPUs, have been developed knowing full well that there are FPGAs around. And it seems that a general purpose FPGA is less efficient when programmed to make it look like a GPU or whatever. Apparently, I can't explain why. I don't really understand the details.
Yeah.
Go ahead.
Well, one comment. There's no such thing as a floating point problem. I could take a problem which is a fully floating point on every computer and turn it almost entirely into an integer problem.
Sure.
And get the same answer.
Sure.
So, I mean, this idea that there's a problem and a way to do it, base, the whole game is in fact to try to change things.
Right.
That's what Anton did. He took an absolutely floating point problem and turned it into an integer. I can do the same with this thing.
Well, and let me come back to this picture. They're not. The problem is not necessarily computational, right? So, okay. Well, let's go on then. So that's computer architecture. At least a little bit I want to say about it. Let me go off onto something completely different, but totally relevant for parallel computing: dependencies. So again, this is going to be a sort of low-level tutorial. Maybe you've studied dependencies in detail. I apologize if this is all very familiar to you. But so here's a set of statements that we might want to execute in parallel. We might want to have, say, two processors doing either one of these computations. So let's look at what the prospects are. So x is equal to, z is set to be a constant in both cases. So x is z plus something, and y is z plus something else. And here z is z plus something. Okay, so this z depends on that. And y equals z plus 6. Now, the normal way of interpreting is that y is this value of z, not this value of z in this statement. So this value of y, or this statement, depends on the outcome of this statement. All right, that's what we mean by dependence. Here, there is no dependence. This statement and this statement could be executed independently. This one has to be executed first before this one is valid in the usual interpretation of that. Okay, so what I want to do is formalize the definitions of this sort of dependence. And this is classical stuff. For any computation, that would be a line of code or a group of lines of code. There is the read set for the computation. That's the set of memory locations from which data are read. And the write set is the set of locations that are written to. And the access set is the union of those two. And there are these three Bernstein conditions, which are the way you characterize whether or not there is a dependence. So you have two computations. Think back to here. I've got C and D. Let's see, is my two lines of code, and I'm trying to figure out, is there a dependence between them? I look at the write set, the write set of one and the read set of the other. If that's non-empty, then there is a dependence, or the read set of one and the write set of the other, or the intersection of the two write sets. So if any one of those intersections is non-empty, then there is a dependence. Now you notice that there is one missing. With two things, there would be four possibilities, and there's one of the four is missing here. So we've got both the writes, the read and write symmetrically. What are we missing?
Read and read.
Read and read. So why is there no dependence on read? What?
It answers itself.
Does it answer itself? Okay, that's a good question. Well, really the answer is because the computer architects made it that way. And it's not really true. You know how dynamic RAM works? You destroy the memory when you do when you read dynamic RAM, you destroy the memory. That's why it's so slow, because when you read it out, it just goes away. And you have to refresh it. You have to send that piece of information back to the dynamic RAM. So it blocks. When you read dynamic RAM, it actually blocks because there is a read dependence. But computer architects have just made it so that that doesn't happen, so that reads don't have any conflict. So you can constantly read. But in fact, there is a blockage that's done at a very low-level hardware level. So we just take this, we have this overarching prejudice that these are the only ones that matter, that we just are not going to go there with that kind of memory. It'd be too complicated to program with that kind of memory. So these are the only three that we have to think about. Now, there's a lot of fine print here. This is the legalese. I won't talk about it, but so you notice that these three are symmetric. It doesn't matter whether I've got C or D. I could switch C or D, and I wouldn't change the collection of those. But you can talk about computations where one occurs before the other, and you could talk about a different kind of dependence. So in other words, you can give a name. Each one of these has a separate name, and so you can parse it out and talk about more fine-grained versions of dependence. And we'll just stick to this. Either it's got a dependence or it doesn't have a dependence, but there is a finer-grained way of talking about it. Let's go back and make sure we can do the calculation. So how do we do it? So where did we say there was a dependence? Here? I guess we said there was a dependence. Now, why is there a dependence? Because in this computation, Z is in both the read set and the write set, and here Z appears in the read set. So there's an intersection between those sets, and that causes a dependency. Here, the read sets for both of these involve just the variable z, and that doesn't appear in any of the write sets, so there's no dependency. And that's all there is to dependence analysis, is looking at the text and seeing where the intersections of these sets are. And it's not the values that you're looking at, but the variable names that you're looking at in those. So this is a set of variable names or locations of memory, not the values of memory. This, of course, can be automated to a large extent, but it's also useful just as a technique to understand whether or not you have a dependence. The dogma is that if there are no dependencies between computations, then they can be done in parallel. I used to call this a theorem, and I realized I can't prove it because there's no formalism for any real programming language to do that, and so I'll just call it dogma. That's the way we believe it. If there is no dependence, you can do it in parallel. If there is a dependence, then you're pretty sure you can't do it in parallel. So that's the way we'll leave it. So dependencies can be different depending on different executions of the code. So one day there might be a dependence, another day there might not. When you do something like this, when you read in I and J, and then you look at these codes, you can't tell whether there is a dependence or not. You need to know where are these locations, and so you couldn't say a priori whether there was or not. So sometimes it's not easy to resolve the question of whether there is a dependence or not. What we're really interested in is loop-carried dependencies. So we have a loop, and we'd like to know if each instantiation of the loop can be done independently of the others, so-called loop-level parallelism. And here's an example you do all the time. This is summing a norm. So we're just computing xi, the sum of xi squared. So we have a variable sum that's accumulating that. We'll eventually take the square root of that if we want it to be a norm. There's a dependence because sum is in the read set and the write set for each iteration. So we can't do the next iteration before we finish the previous one. So how do we get around that? Well, what we can do is we can have two partial sums and compute them at the same time. One will do the evens and one will do the odds in the indexing, and in the end we'll put that together. So that's a way to get more computation without dependence, and you can take this to the extreme. I'll show you in a second, and I'll just give you the results. What does it do for you? Well, with different architectures, these are sort of some of the older historical architectures, but what you see, depending on the so-called number of splittings, here we've done a splitting of this loop, you can get a significant increase in performance because you've broken this dependence. So here we're thinking of this as just being a sequential architecture, but this dependence has a significance because these are all pipelined architectures. And unfortunately, it didn't do well on the Cray architecture. The Cray vector architecture loves this kind of code, and so it was bad for that. So what can you do? Here is, if you wanted to do k different splittings, it's very simple. You're just going to have k different partial summands. The middle part of the code looks the same, except you're doing it now for each j. These can now be all done in parallel, and you put it together at the end. This is now beginning to look like our summation problem that we talked about initially. So, and that's what leads to this big increase in performance, and you can see things like the old IBM architecture really took a long time before the benefit was finished on that. Okay, so to formalize that, it's a little bit complicated. Let me just go through this quickly. You need to take loops in normalized form. So you don't want it to start an arbitrary place. You always want it to start at 0 and the stride to be 1, and so you can always change your loops in that way. You want to consider multiple loops. We'll look at one in a little bit later that has at least 2 loops that are nested, and so that gives you multi-dimensional indices. The iteration space is multi-dimensional. these are called multi-indices, integers in n dimensions. There's a natural order on it, the lexicographical order or dictionary order. And so when we talk about whether one computation comes before the other, we just use that lexicographical ordering. And now you can define what you mean by a loop carried dependence. Because what you do is you say, well, if I've got two parts of a program and I've got two different indices, I can take the part S with index I and part T with index J, and then I just go back to my original definition of dependence. So I say there is a loop carried dependence if these three Bernstein conditions, one of those intersections is non-empty for these distinct computations. And of course, we're interested in cases where there are no loop carried dependencies, and that is what we were doing here. We were in this way, we were breaking dependencies by having each of these partial summands be independent in there, and that removes that dependence. Let me do one more example that shows you a technique called privatization of variables. There are some things, like this simple code here, where I've got a temporary variable that's in both the write set and the read set of each loop index, so that gives me a loop carried dependence. But when you think about it, you say, well, but that really isn't this serious thing. This means I. This is just a different way of putting I here. I don't know why whoever wrote this code, but anyway, somebody did, and now there's an apparent dependence. But it's not an essential dependence. All you've got to do is say, make that variable depend on the loop index, and now that breaks the loop carried dependence. And this is something that comes up in shared memory programming a lot, so there are languages like in OpenMP and other shared memory languages before that where you can declare this variable to be private, and what it does is effectively achieve this without you having to put in the variable names. But it's not that big a deal to put the index dependence, the explicit index dependencies in there, and that removes the dependence, and you're off and running. Okay, so let me just, I'm running low on time here. Let me just give a more serious example that pulls together a lot of these ideas. And that's with Gaussian elimination. So Gaussian elimination, here I've written a system of linear equations. You've probably seen this in many forms, maybe in this form exactly. So I have a system of linear equations, and I do elimination to solve those equations. I take a particular row of the matrix, and I subtract it times a suitable multiple from the other rows, and that's this simple code for doing Gauss elimination. There are these so-called multipliers here that actually have some significance on their own that get involved. That's just the thing that makes it so that you can eliminate the numbers in a particular column in the matrix. Here's what the iteration space looks like for that algorithm. There's a variable k that's proceeding here on the outer loop. It's a triply nested loop, so it's a three-dimensional iteration space. The inner two loops, where we would be most interested in the dependencies, there will be dependencies on the outer loop for sure, but on the inner loop we might be interested in whether there are dependencies, and that's the inner two loops, the iteration space for the inner two loops. This is some sort of trapezoid going into the board. Let me just say a little bit about what Gauss elimination does in case you haven't seen it. In the end, you get these so-called multipliers, which were called L in the previous slides, and you get a triangular system in the end that's very easy to solve. And what you realize is that what Gauss elimination does is perform a matrix factorization. And with this matrix factorization, you can solve the original problem by just solving something involving that upper triangular matrix U. So that's what Gauss elimination does. And here are its basic properties. The most important property is there are no loop carried dependencies in that innermost loop. So let's just look at that, because that's the most important thing here. So I'm saying that in this These are the innermost loops. They're doubly nested, but there's only one line. So to look at dependencies, we just have to say what's in the read set and the write set of this. So Aij is in the read set and the write set, but it can never be the case that those indices ij are equal to kj for different values of I and ij and k, because look, I and j are always k plus 1 to n, so they're always bigger than k. So the value here can never be equal to the value there. There's no read and write dependence on that. So this can be done, these inner two loops are totally independent and can be done in parallel. Okay, there are many different ways to do it. I'll probably come back over this a little bit, review it next time, but just to jump over it, here's a standard way that can be parallelized by having each processor own a certain number of columns of the matrix, and the computation is what we're doing is we're taking this square of computation in the iteration space and dividing it perfectly among p processors, and then there's a cost of communication. And from that, you can do a speed-up analysis, efficiency, and scalability, and you'll see that this is a scalable algorithm, so this pulls together all these ideas about efficiency and scalability, and I've got some data to verify that does work. So with that, I'm going to, yeah, go ahead.
Oh, you're touching right.
Okay, so then we also talked about memory scalability, so we'll look at that for this algorithm. And then I'll move on to what seems like a simple problem. Certainly for sequential computation, solving a triangular system is trivial. That was the whole point of Gauss elimination. But this actually gets to be interesting in parallel because it appears to be an essentially sequential description. And so that's when things get a little bit harder. So that's what I'm going to get into in detail next time. But I will go back and just review all of this. But this pulls together a lot of the ideas about the scalability of it. And somewhere here I seem to have lost the key observation that the reason that Gauss elimination is so scalable is that the amount of work that needs to be done at each step is quite large. So the work-to-memory ratio is actually proportional to n, and n could be quite large, and so you get better and better work-to-memory ratio. So it's kind of it's too easy a problem, but we'll go over that in more detail next time.